In the following video, we are going to focus on examining the characteristics of even degree and odd degree functions. We're going to start first with even degree functions. Now, even degree functions mean that your leading term is going to have an even degree. It's going to either be squared, fourth power, sixth power, etc. So we're going to be dealing with quadratics, quartics, and 6th degree, 8th degree polynomial functions. When you're dealing with an even degree function, both ends of the graph are either going to be pointing up or they're going to be pointing down. So even degree functions, your end behaviors are going to be pointing in the same direction for it. And you can realize that if you think about how quadratics were U-shaped. You know, they're pointing in the same direction, whether you are opening upwards or you're opening downwards for it. We've learned back in previous lessons that zeros are your x-intercepts. It's how many times the graph crosses the x-axis. That's the number of zeros. And your end behavior, which we're going to examine future part of this video, is determined by the leading coefficient and the degree. And what that means is since this is opening downwards, that's going to mean something is going on with that leading coefficient. Since this is opening upwards, same thing, something's going on with that leading coefficient. So that's an even degree function. What we need to get from even degree is that the ends point in the same direction. Now, if we examine odd degree functions are going to point in opposite directions. And you think about odd degree, I mean, first ones many people think of is, okay, you have third power, then you have fifth power, seventh power, but you keep on forgetting there's also the first power being linear, third power being cubic, fifth power being quintic. Linear even points in opposite directions because a positive slope, this side's pointing down, this side's pointing up. A negative slope, this side's pointing down and this side's pointing up. So even linear functions follow this odd degree behavior. Again, zeros are your x-intercepts, how many times the graph crosses the x-axis. And our end behavior, which we will be examining, is determined by your leading coefficient and the degree. Particularly since this one is rising to the left and falling to the right, that means something's going on with the leading coefficient. If I were to kind of reverse this graph and have it falling to the left and rising to the right, that's going to mean something's going on with that leading coefficient. And that's what we're going to examine with the end behavior. So odd degree functions point in opposite directions, while even degree functions point in the same direction. So here's an outline of the even degrees. We have an example of it opening upwards and downwards. If it's opening upwards, we learn with quadratics, which is an even degree, that means the leading coefficient is positive. If it's opening downwards, it means the leading coefficient is negative. That works for all even degree functions. You see this is x squared quadratic. This is negative x to the fourth, which is a quartic. So if it's opening, if both sides are pointing in the same direction up, it's a positive leading coefficient. If both sides are pointing in the same direction down, it's a negative. Now, end behavior is a little interesting. For end behavior, you need to examine what's going on in the graph. How does the x values relate to the y values? And so if I look at my left side end behavior, so I'm focusing on this part right here, my x values are decreasing forever. So x is approaching negative infinity. And as your x values decrease, you notice the graph is rising up. That means your y values are increasing to positive infinity. If you focus on the right side, my x values are increasing to the right. So they're approaching positive infinity. And as my x values increase, you can see this curve is pointing up. So are the y values. The y values are increasing. So the right side behavior is x approaches positive infinity, y approaches positive infinity. If you look at the negative leading coefficient, the left side behavior, your x values are decreasing, x is approaching negative infinity. And as the x decreases, the curve is pointing down, so does the y's. Y is approaching negative infinity. As x approaches positive infinity on the right side, The graph is pointing down, y is approaching negative infinity. The domain and range, domain for your even degrees is all real numbers. Your range is based off of your minimum value here. We see that our range cannot go below this point, so y is greater than or equal to that minimum point. And here y is less than or equal to, since it opens downwards, that maximum point. So that's an even degree function, both positive and negative leading coefficients. Let's examine our odd degree functions with positive and negative leading coefficients. So if we have a positive leading coefficient for an odd degree function, it's going to fall to the left and rise to the right. If we have a negative leading coefficient, it's going to rise to the left and fall to the right. That's how our leading coefficient determines our end behavior. As x approaches negative infinity on this left side, the curve is coming down, so your y is approaching negative infinity as well. On the right side, as x increases, x approaches positive infinity, your y is increasing and approaching positive infinity as well. Domain and range, the arrows go on forever, are both all real numbers. For the negative leading coefficient, your x values are decreasing on the left side, so x approaches negative infinity. As that goes on, your y values are increasing, so y approaches positive infinity. Right side, x increases forever, so x approaches positive infinity. The graph is decreasing, so y approaches negative infinity. Same domain, same range. So this video was just meant to introduce the idea of even degree, odd degree functions, their end behavior, and how the leading coefficient determines the direction that the graphs are pointing for the polynomial functions.